All right, welcome to section 4.3. We are going to be doing some exciting graphs today. So we are going to first learn how derivatives affect the shape of graphs. Okay, so here we go. So up until this point, we know how to graph like your standard functions, like your rational functions and some square root functions and some logarithmic functions. But we're gonna start graphing some really crazy combination functions, right? So maybe like the natural log of the sine of x, stuff like that. And we're going to do it all with derivatives. So let's do a quick introduction. Let's look at a graph, and we'll just stick with a polynomial. We're familiar. And let's do a little bit of exploring. We're going to look at the increasing and decreasing parts of our graph. Okay, so if we wanted to identify the increasing parts, right there. And right there, and then we have the decreasing parts, be right in here. All right, and then we want to see if there's anything we can relate to the increasing and decreasing parts with the derivative. Well, the derivative is slope of the tangent. So let's start by drawing some tangent lines in the increasing and decreasing parts. And when we're drawing the tangent lines, what do we notice about all of those slopes? All of the slopes, or all of the tangents, are increasing, so they're positive. All right, so the slopes, which are the derivatives, are positive. And then on the flip side, if we were to focus on the decreasing parts, and if we were to draw all of our tangent lines at those points, they're all decreasing tangent lines. So the slope is negative, so it means the derivative is negative in those points. So just using the derivative, we can tell where our function is decreasing or where our function is increasing. Okay, and then putting those concepts together, that's called the increasing-decreasing test. So that's the first test we're going to run when trying to graph these functions. And we sometimes call it the ID test for short. ID, it's an acronym, ID test. Okay. So this is what we have to do. So to do the increasing-decreasing test, we have to look at the derivative. And we have to figure out where the derivative is positive. And if the derivative is positive on an interval, then f is increasing on that interval. Okay, and then likewise, if f is negative, if the derivative is negative, then f is decreasing. All right, the ID test. So let's look at an example. And we're going to go to number 10a. We're not going to do all of 10. Well, at the end of this lecture, we're going to do all of 10. But for right now, we're just going to do number 10a. And 10a says to find the intervals on which f is increasing or decreasing. And our function is this, 2x cubed minus 9x squared plus 12x minus 3. Okay. So again, we're going to find intervals where f is increasing or decreasing. Okay, so by the ID test, to do this, increasing, decreasing test, to do this, we have to figure out where our derivative is positive and where it's negative. So our first step is going to be figure out what the derivative is. All right, so 16x squared minus 18x plus 12. Okay, so where our derivative is going to be changing is essentially is at the critical numbers. So we have to find the critical numbers because those will separate where our derivative is going to be changing signs. So we're going to find the critical numbers first. Okay, and then let me just show you here on our little graph up here. Our critical numbers are where the local mins and local maxes happen. And we could see that's exactly where they change sign, and that's where the derivative is 0. That's what a critical number is. All right, so let's set our derivative equal to 0 and figure out where that happens. All right, so we're solving a quadratic. One side's already 0, so I think we can factor this. I'm going to take out a factor of 6. If it wasn't factorable, we could always use the quadratic formula. All right, and so two numbers that multiply to positive 2 and add up to negative 3 are negative 2 and negative 1. Okay, so our critical numbers are x equals 2 and x equals 1. All right, and I want to point out too, remember critical numbers are when the derivative is 0 or where the derivative is undefined. And the derivative is defined everywhere, so that's not our case. We just have to worry about where the derivative is 0. So we now have where our derivative changes, or the critical numbers, I'll just say critical numbers. They're 1 and 2. So now we have to figure out where our derivative is going to be positive and where it's going to be negative, okay? And 2 and 1 are going to be dividing those intervals, all right? Because those are the zeros. So after 0, it's either going to be negative or positive. After 0, it's either going to be negative or positive. There's a couple different ways to do this. You can always think of the shape of the derivative. Oh, hold on. Let me do one other thing. It's really important that we label all of these real number lines. So I'm going to put f prime because we're dealing with f prime. F prime is the shape of a parabola because it's quadratic. And it's a positive parabola, so it's going to look something like this. Let's try to draw it very lightly. So just based on the shape of the graph, we know that the intervals are going to go positive, negative, positive. So that's one way to do it. That's if we know the shape of the graph. Sometimes these functions get crazy, and we're not going to be able to know the shape of the graph. In that case, we can always use test points. For instance, 0 is in this interval right here. If I were to plug in a 0 into our derivative, we would get positive 12. All right, it's positive 12, so it's a positive number. We could do the same thing right here. We could plug in something like 1.5. All right, and then I'm going to go the factored form for this. Remember how we can just focus on factors? Right, if we plug in a 1.5 in the factored form, 6 is a positive factor. Let's see, 1.5 minus 2 would be a negative factor. 1.5 minus 1 would be a positive factor. So let's see, we would have one negative factor. That would make the whole thing negative, right? That's what we have right there. And then last interval, we can choose a test point. Same thing, the first factor would be positive because it's 6. And then 3 minus 2 would be positive. 3 minus 1 would be positive. So all of your factors are going to be positive. All right, so we can also use test points too. Okay, but now that we know all of this, we can figure out where the function f, remember we're using the derivative to give us information about our function f, where f is increasing and decreasing. And f is increasing on the intervals where the derivative is positive. All right, so on, what colors did I use last time? Blue and yellow and green. So on the positive intervals, that's where our function's increasing, and where the derivative is negative, that's where the function is decreasing. So f is increasing on, let's see, that first one is negative infinity to 1, and make it an open circle, or open interval, and then 2 to infinity. Those are those outer two intervals. And then we can join intervals, we can unite them with a u. And then f is decreasing where the derivative is negative. So between 1 and 2. Okay, excellent. So there you go. There's the ID test. I want to use that example again. All right, we discovered, positive, this is f prime, positive, negative, positive. I'm going to draw f in, I'll draw f in blue, okay? So we're increasing here. Function f is increasing, decreasing, increasing. So f is increasing till 1, then decreasing till 2, and then increasing again. Do you guys see that? All right. When I did that, look what else we discovered. When I did that sketch, this is f. We're using the derivative to tell us about f. We just discovered a local max at x equals 1. Remember that, we're going to use it later. And we also discovered a local min at x equals 2, just using the derivative. And that's called the first derivative test. So let's write out what the first derivative test is. All right, so let's suppose that c is a critical number of a continuous function f. So suppose that c is a critical number of a continuous function. Okay, well, I don't want to write that. So that's the criteria, and that's what we just did. We found all the critical numbers of a function f. So it's in 3 parts. So if the derivative, and you can look back right here, if our derivative changes from positive to negative at that critical value, it's a local maximum. So if f prime changes from positive to negative at C, of course, the critical number, then F has a local min at C. Excuse me, a local max at C. All right, and then also, if F changes from if the derivative changes from negative to positive at C, the critical number, then our function F has a local minimum. Let's write that. If F prime changes from negative to positive at C, then F has a local min. All right, and then finally, there's cases where there's no sign change. So F prime is either positive to the left and right of C, or both negative to the right and left of C. Then F has no local min or max. So I'll draw a picture of that one right now. All right, so if you guys remember the graph of x cubed, it goes something like this. Right, this is f of x equals x cubed. And then right at 0, we have a critical number because the slope is 0, okay? But there's clearly no min or max right there. And if we take a little bit more of an investigation, the derivative is 3x squared. So we can see that x equals 0 is going to be the critical number because f of 0 is 0. Okay, and then if we were to look at, here's 0, f prime. If we were to plug in a number to the left of 0 into our derivative, it's going to be positive. If we're going to plug in a number to the right, it's positive because 3x squared is always positive. So there's no sign change to the right and left of C. And so we can see that's not a local min or local max. Okay, so no local min or local extrema at C equals 0. All right, so let's practice finding the local min and maximum in our next video, part 2 of this section.